Welcome back, everybody. Happy Halloween. So hopefully everybody had a good weekend. Looks like tonight's going to be pretty bad outside. I guess I'll buy less candy this time. I'm always like stocked up with tons of it. Only one thing happens with it, so don't buy less. Okay. Midterms back, I think, on Wednesday. I'm almost done with all of them, but still kind of like scrubbing over them a little bit. I'll have some messages about the midterm next time. So I think a lot of you can recognize where you struggled and had some problems. So I'd be trying to work through those problems again if you can remember up. But I will be giving an opportunity for you to redo the midterm, turn it back in. But let me turn it back to you first and discuss the grades. The rest of the class is minus the hypothesis testing bit that we'll get into next time. It's basically the same thing, but we're scaling up the examples and using them in layers of problems. And so you'll want to be able to do all the old stuff that you've learned how to do already. So definitely learn how to do that before we move into more complicated examples. Okay, I have a homework that's out. Homework 4 is out. I put a date on it that it would be due on November 16th. We'll see how that date holds up. I do need to get into hypothesis testing so that you can complete the homework. Last time on the last homework, I asked you to find the Jeffreys prior in a binomial example. I get this question all the time, like, is it just one realization from a binomial? It can be. N's already in there. So that's like n realizations from a Bernoulli. It has the same information about P. So I don't really care when you do it. If it's, you have m of these things, you know, where there are n Bernoulli coin flips, it'd be the same thing as doing n times m Bernoulli coin flips. So usually when I'm playing around with binomial, I just give you one data point. And so, but it has lots of asymptotics built into it. N is there. Anyway, you can work through that and provide that answer. It's basically plugging it into one of these equations right here. You'll work it out, and both will work. So both of those forms will work. So I think a good problem to do in terms of Jeffreys is just plug in all the distributions you've been playing around with and work out Jeffreys priors real quickly. It's a good calculus exercise. So basically, how do you study in a class like this, a probability class? You just change the distributions and then try to work out everything out. And so when you get stuck and you can't do things analytically, then you're thinking about the Monte Carlo stuff, you know? And so anyway, those would all be good practice problems. Let me just walk you through this real quickly. So homework 4 is out. It's accompanied by a data set as well. Both those links are here. The homework does say 2020 on it, so this is an exact replica of a homework that I've given previously, so I didn't change that. So here's all the problems. So problem 1 is going to be the wrap problem right here. So this is the same model that we've been talking about for a couple weeks now. What I'd like you to do is implement your Gibbs sampler for everything. So first thing, I just want you to write down all of your full conditionals for everything. If you're having trouble with that still, feel free to ask after class or something like that. We could probably do a review session next week, so that would be another place where you can ask. But if you're hung up in the meantime, maybe send me a note on Slack and maybe we can append a lecture. You know, if all of a sudden it's like you're just not there with the full conditionals. I don't think it's anything more complicated than we've ever already done, but if you get it wrong, it might be a little bit mind-numbing if you're trying to code it all up and you're saying that it's not working and you don't know where your error is. Is it in your modeling assumptions, or is it in your code? Or is it where you put a brace somewhere wrong? So we can go through it. So if there's any interest in me covering the full conditionals in more detail, you can send me a note. Also, I'll point out on Slack, I do not check the instant messages. So I checked them finally yesterday. So, and I saw that there were a few on there. I don't look at those. If you send me Facebook messages on instant message, I don't check those either until like 6 months later. So I do check my email, and I do check my texts as well, but I don't think I've given everybody my telephone. So email is better, but if you just have some general questions, you know, might be helpful for the whole class, you can put them in the general comment on Slack. So, and I do check all of those links. Okay, so I will point out in Gelfand and Smith, they parameterized things slightly differently than the parameterizations we're using. So you want to think about what are their distributions and transform them into distributions that you're using. So they use proper priors throughout everything. And so that means that they have hyperparameterizations that probably matter. And so one of the questions here that you can investigate is, do their hyperparameterizations make sense? How much do they impact their conclusions? And I'll give you a hint, I don't think it's totally negligible what they've done. Saying that, they did use that problem to kind of describe Gibbs sampling, so there's a lot of utility in that write-up. So all of that stuff was brand new back in the early 1990s. I did give you the data set also, and it's right here. So it's in that text file. So these are just the 30 by 5, so there's some number of time points and then some number of rats. This is actually time here, and these are your number of rats in that direction. Okay. So you're going to plug that in to your Gibbs sampler and plug that in for your W's, or whatever this variable is. So I did change it a little bit. I used an X here. So that Xij is your WIT that we put on the board before. Next problem. This is going to continue that Cauchy problem that you're doing. I will point out that the way the data is generated and the model that you're fitting are different. So let's just walk through this. You're going to generate data from a Cauchy with this not covariance matrix, it's a scale matrix. So it's not covariance because variances don't exist for Cauchy. So, but it's something like that. So basically this is going to describe some scatter of points that is positively associated with each other. So I guess we'll look at it like this on the board. So the slope of everything might have something to do with 0.8. So I'll let you work through that. This is just you're gonna sample points just like you did in the last homework, X, Y pairs, and now you're gonna fit that Cauchy regression to that cloud. Let me just ask a quick question. Where is, the data is being generated under some model and then we're fitting some other model, this regression model. How do they differ? Are they the same in disguise or are they a little bit different? Okay, let me just ask the question this way. If I were doing a bivariate normal sampling and I sampled a cloud of points bivariate normal, and then I fit a standard regression, y on x, how would those two modeling assumptions differ?
Because in the standard modeling, you're assuming that there wasn't an error term, which is just associated with y.
Yes, exactly. So the y's are where the residuals are. In this other thing, what we've sampled, it also throws things out in the x direction and y direction simultaneously. So they are a little bit different, but you do see outliers with those two different behaviors. Obviously, outliers that run in the same direction as your line don't have a lot of leverage. If you've taken a regression class, you'd be familiar with that. And so we're kind of covering two different cases, is where points are outliers with potentially high leverage and potentially no leverage. So anyway, we're kind of imagining everything was bivariate in the first place, distributed, and then we're fitting this model that assumes just the y's or the random thing. So you're going to fit this Cauchy regression to this type of data. So it's very similar to the modeling assumptions, it's just the directions of the error. Keep in mind in regression, in a lot of cases we assume that the x's were fixed. So, but we want to create everything in a random manner. Okay. So you're going to fit that Gibbs sampler that you wrote down last time. So you're going to have a full conditional for your betas, you're going to have a full conditional for your variance, and you're going to have these full conditionals for all of your gamma i's in that mixture representation of a Cauchy. I will point out the reason you do it like this versus writing down the Cauchy likelihood, if you did do that, the Cauchy likelihood is unfactorizable. And so if you had a lot of data points, how many data points did I ask for here? 1,000 data points, you'd have some serious numerical instabilities, that you would have a product of 1,000 terms. And you'd have to deal with that. And taking a log over it isn't just going to solve it instantly, because you have the 1 plus term. So you have in a t distribution, you have this thing raised to some power that has something to do with the degrees of freedom, and then you have 1 plus some quadratic term. So if that quadratic term is numerically unstable, i.e. you have bad starting conditions or something like that, or a lot of variability in your terms, which you do in this, then you're going to get some numerically unstable terms. When you take the logarithm of it, you're going to have log of 1 plus that thing, and the log's not going to be directly hitting that quadratic term. There is a way to numerically fix that and to take into account that you can compute the log of that stably, but you can't just do it algebraically in just one line and fix it all up. So the correction to this is to use this mixture representation. So you'll code up that Gibbs sampler. This problem we haven't talked enough about, so we need to get into hypothesis testing. So hold off on problem 3, but I asked you to generate data from this normal right here, but I'm going to have you do it where you're going to have 4 different mixtures of this normal. 400 of the data points are going to come with mean 10, 200 of the data points are going to come with mean 15, 300 data points are going to come with mean 17, and 100 data points are going to come with mean 20. So you're going to be sampling these 1,000 different points, but they're going to be coming from different normals. This problem is created just to show off the differences between what a Bayesian's doing when they're hypothesis testing and what a non-Bayesian's doing if they're hypothesis testing. And there's a big difference between those things. So we need to go over quite a bit of this. But what you're going to be doing is you're going to be computing p-values for these corresponding hypotheses, and you're going to be computing posterior probabilities for those competing hypotheses. We need to talk about what's different. I'll just give you a heads up. What the Neyman Pearsonian does, the classicist, if you will, they're calibrating error rates, but what they're really going to do is they're going to try to figure out what the probability of your data or more extreme data under a null hypothesis is, which is very different from the probability of the null hypothesis itself. And what a Neyman Pearsonian is going to do if they tested hypotheses like this, is theta 10, or is theta 15, or is theta 17, or is theta 20, I think that they actually get a better answer than the Bayesian will come up with if you do the blind Bayesian thing. It would say, no, it's none of these models. So if you ended up building the likelihood function up from all of this data and you tested a hypothesis, did it come from theta is equal to 10? Probably you would reject that hypothesis. Nope, that's not it. The data looks different from that. And it is different. It's substantially different. It didn't even come from one normal model with one mean. It came from 4 normal models. The Bayesian, when the Bayesian computes something and tests the wrong hypothesis, they're going to be saying which one of these looks closest out of the 4 competing hypotheses. So they're going to say you have an entire universe of hypotheses. It's either theta came from 10, theta was 15, theta was 17, or theta is 20. And it's going to say out of all those candidate choices, which one is closest to being reasonable. And so the Bayesian is always going to do that. In this example, all the hypotheses are wrong. You probably want to reject them all. And so the real problem with this is you've written down the wrong model. And so just a heads up for the next next homework, I ask you to fix this. And so what you really should be doing is mixture modeling and saying, actually, it probably comes from 4 different things, and we need to estimate what those 4 things are. So again, this problem, problem 3, is just set up to illustrate the differences between a Bayesian and a non-Bayesian. And for once, the non-Bayesian probably wins this argument, but it really is a question about the question being asked in the first place. So this hypothesis is entirely nonsensical. Hopefully you understand that. We'll talk about it more when we get into hypothesis testing. So in the next lecture, we'll start up with that. This is the same sort of thing. This is an easy calculus problem once I tell you how to do it, but what you're going to be doing is you're going to be computing the posterior probability of null hypotheses. And that's what a Bayesian is always doing. And so it's always going to be compared to whatever you assumed in the alternative space. We'll point out, for those of you that are naming Pearsonians, the only place you use the alternative is in the tail direction. And so you never actually do an explicit comparison to the alternative. So if you do, you're coming up with the whole power curve. That's what the power curve does for you. And then you're considering all the alternatives. And the big question Bayesians will always ask is, how do you put that all together? Lots to talk about that. This is probably the most contentious thing in all of statistics, this conversation. Problem 5 you can probably do if you know what a p-value is. This is an easy exercise that's in every inference book out there. And so you can find this lots of places. Under the null hypothesis H0, you can prove that the p-value has a uniform distribution. And so we'll be talking more about that. But if you've ever taken a Stat 101 class, they probably drilled you on this. So they probably didn't tell you why it all works, and they just turned you into robots. So come up with a test statistic, compute P, make a decision. So you're not thinking in that process at all. Okay, more on that later. Hopefully I can do that some justice, and at least 3 of you will understand what the difference between a Bayesian and a non-Bayesian is, and why hypothesis testing is such a loaded thing in the first place. You have about 2 weeks to do that. You might have to extend some of the deadline on some of these latter problems right here. I will point out also, there's a lot of numerical instabilities in computing both the Bayes factor, the posterior probability for this incorrect hypothesis test, and also for p-values there could be some numerical problems as well. And so that is intended to be part of the problem. And so what I mean by that is you probably want to start that early. So what I would do as a first step is just generate the data and look at it. And so that's step 1. You can do that pretty easily. So just generate 400 points from a normal with mean 10 and variance sigma squared. I don't tell you what sigma squared is, but if you'd like me to pick a value for you, 5 will work just fine. So. Okay. More to say later on that. Let's get back to Jeffrey's prior. So I'll point out who this guy is right here. And I'll just point out real quickly, his name is Jeffries, like that. This is his name. It has an S on the end. And so if you were going to put an apostrophe, you'd put it after. So we don't do this. I don't know why we don't do that. Probably make everything a lot easier. I think that's fine. But yeah, it seems to at least follow all the rules, you know? So grammatically correct. Who makes these rules? It's like that. So it is Jeffries's prior. So you could also call it the Jeffries prior. That's fine as well. But if you put the apostrophe right there, I'll know that you're aware. So I do see seasoned professors do that sometimes. Does anybody know who Jeffries is? Does anybody know his first name? You can say it's a first name. It's Harold. Old Harold. Harold. We've encountered him before, so this was in this manuscript that we at least talked about confidence versus credibility. And so there's this argument, could Jeffries name it and Fisher have agreed? And so Jeffries is encapsulating the Bayesian school of thought. Jeffries is what we might call an objective Bayesian. So he's thinking about properties of the posterior and coming up with priors that have certain guaranteed properties in the posterior. He wants to be in some sense objective. He understands there's a lot of arbitrariness that goes into an analysis. For instance, Do you want to do analysis on sigma squared, or do you want to do analysis on phi, the precision parameter? And Jeffries is clairvoyant enough to know that it shouldn't matter which one you're talking about. There's a one-to-one relationship, and so you want to preserve whatever properties you have, whether or not you're analyzing phi or sigma squared. I will point out that in a lot of statistics classes, when you do transformations on things, it totally matters. So you might not be thinking about it. You might just be doing it for convenience. So for instance, if you're running a regression model and the error terms don't look normal, you might sit there and start transforming the x's and the y's until everything looks normal on everything. The question is what did you just do to all your variance bounds on everything? If you're building a predictive model, maybe it doesn't matter to you. So you get data, you transform it in a particular way, you want to monitor a process, maybe you can do things that are convenient for you. Saying that, if you're going to try to infer and interpret everything, it matters what scale everything's on. And so you can't just back transform all of your bounds on your confidence sets in any arbitrary regression analysis. And so you need to be a little bit more thoughtful about everything when you do that. So what are we really trying to do with things like box-Cox transformations? Is we're trying to cram everything into a normal model. And so we want everything so that our lives are easy, but we need to be a little bit more thoughtful about what do our inferences mean. So Jeffries is a physicist, and he understands this arbitrariness can come into a lot of analyses, and he doesn't want to explain arbitrariness. So Jeffries is looking for a way to unify what we all do and not just come up with our own subjective priors. Now, I am an advocate of subjective priors if you have good subjective rationale and you can back it up. So if you did know something about the parameter that you were trying to estimate, and you wanted to include that in your analysis, you might control some hyperparameters in your distribution for your prior, and that might contain that information. I think that's a good idea if you have good rationale for doing it. We're not doing a big case study of lots of problems in this class, so we haven't really talked about how to do that. But there is a field called elicitation, and it's basically how you put a scientist on a couch and you try to get them to answer a series of questions so that you can calibrate your prior to their subjective knowledge. I'm not a big fan of that, so I've never seen it actually work. So I am a big fan of things like meta-analyses, where it's like there's previous studies that are done and you can combine these studies, and you might want to see what's the added benefit of your new experiment over that study, and you might want to combine both things. And so you might calibrate information from a previous study in your prior, and then use that to come up with your updated posterior inference. So you're kind of thinking of a sequential nature of things. People have some knowledge, you do another experiment to refine that knowledge. I think that makes sense. So how you combine knowledge, sometimes the subjective way of being a Bayesian can be very useful. But still, on to Jeffrey's point, if you didn't know anything about the parameters and you're going to come down and you're going to try to place priors on them, you want to do something so that if somebody else came into the analysis and maybe came up with the same model, it's a one-to-one transform of your model, you would want them to have methods for coming up with priors that at least agree with what you're doing. And so what Jeffries came up with was this. So Jeffries said, Jeffries' prior is going to be the information to the half power. And so this is the information, and very often we can write down the information like this. The half power remains the same. So this is just the information to the half power. The very often part is just when Fubini's holds. That means that I can interchange this derivative right here with the expectation. You might like it a little bit more in this form because you don't have the squared term. And it just means that I can take this second derivative and pull it outside of the expectation. So very often, it's just that I can interchange these two things. I can interchange my order of derivatives, my order of integration and derivatives, my order of integrations, all of that good stuff holds. So, and we proved that last time. We could even see that for this version of the information to be that version, we needed to do the interchange. So that's my favorite type of proof, where it tells you the conditions in the middle of the proof. So it's just a calculation. Okay, let's look at an example. So of what this might look like. So let's just look at, we're going to have x's, xi's. I'll say x comes from a normal distribution with mean mu and variance sigma squared. And I'll say sigma squared is known. It's a known constant. So we'll just go back to the first week of class and think about this prior that we were trying to develop for mu. We'll see what Jeffries has to say about it. So we said lots of, maybe intuitive stuff. It's kind of a loaded word. It's like once you understand something, it's intuitive, But we at least came up with some intuition that maybe the flat prior was the right thing because this was a shift parameter, mu. So if I just write down what px looks like, given mu, and I'll get rid of the sigma squared right here because it's just a number. So more commonly, people would write things like that down. So I've exposed you to lots of different notations expressing different things. So square root 2 pi, there's a sigma in there, that's just a number, e to the minus 1/2 x minus mu squared over sigma squared. And so you can look at this and see that with respect to x, mu is just shifting that distribution around. I want to point out just real quickly, coming up with flat priors is not an invariant rule. And we saw this before. And so let's just write this down because it's sometimes a little bit confusing for people. So flat priors in general, I think that's the operative word, in general. So generality over all collections of all things. In general, they're not transform invariant. So we've already established this. So if I ended up doing something like this, if I had some prior on mu, so I might do something like this and say, I'm going to say it's proportional to 1. And so let's just say experimenter 1 chooses this prior. Some other experimenter thinks, I don't like this representation. So experimenter 1 playing around with this. And experimenter 2 says, I don't know, I write down my normal distributions a little bit differently than you do. They write it down like this. X minus 1 over psi over sigma squared. And so 1 over psi is a shift parameter. It shifts things around, but psi is not a shift parameter. Psi is not the mean. 1 over psi is the mean. And so this thing used to look like mu, and I just plugged in some other form of it. So if you think about this, they're the same likelihood functions. So I can move this around by changing mu. And I can move this around by changing phi. Of course, the rate at which I change it is different. So, but when I change phi, I change 1 over phi, and so I should be able to shift that all over the place as well. But the behavior of that is different. And so if I chose a 1 unit change in mu, it would shift this around by 1 unit. But if I picked a 1 unit change in psi, it wouldn't change that whole distribution around by 1 unit. If I changed 1 over psi by 1 unit, then it would move that distribution around by 1 unit. But changing psi by 1 unit is different from changing 1 over psi by 1 unit. So those are different things. And so if experimenter 2 misunderstood what I said in that first couple weeks of class, they might be inclined to say, I'm going to make my life easy. I love multiplying by priors that are proportional to 1 because I don't even have to think about them. But experimenter 2 might do something like this. proportional to 1. And that would be totally different. So they would come up with different analyses if you did this. Now I will point out, if experimenter 1 put a flat prior on 1 over psi, they might agree with each other. So that's a different thing altogether. And so I'll just point out that if we change, if we do a transformation of variable, on this, we did this before. So if I took what experimenter 1 was thinking and I tried to map it over to the space that experimenter 2 was living in, I might write down, and I'm going to do the same thing. I'm going to constrain mu to be positive just to make everything 1 to 1. So just to show you in the positive space it's different, in the negative space it's different as well. So we might do something like this. Psi is equal to 1 over mu. 1 over psi is equal to mu. Same thing, it's all together. And so I could take my prior on mu and try to convert it over to a prior on psi. So this is going to be proportional to, as soon as I have a proportionality sign right there, I'm not going to be able to fix this up with an equality sign, so I'm going to use the exact same thing. So this is going to be pi mu 1 over psi. So this is just my inverse transform, derivative 1 over psi for d psi. So this thing is still proportional to 1. Right there, I take that, I plug it in, but that's a constant function, and then I do this. So this is going to be psi inverse. So I'll bring down my exponent, and then I'll decrement my exponent. And so this is going to be proportional to 1 over psi squared. So if experimenter 2 wanted to use this new parameterization, and they thought that experimenter 1's prior was good, then this would be the implied prior that they would work with, at least in the positive space. And so it wouldn't be this. This is a different thing. And so when I transform things that are flat, they're not flat anymore. So to say that flat priors are an invariant rule, this is a contradiction to that. When I transform them, they're not flat anymore. There's something that are different. There's something different there. So Jeffries does this. So Jeffries says, whatever parameterization you're working on, just plug it into this equation. So let's do that. So I'm going to plug in, I'll say the Jeffries prior for mu is going to be proportional to I mu to the half power. We'll just work this thing out. So I mu is going to be equal to, I'll write it out using this one, log, and then I just take this function that we've written down and I plug it straight in. So this is going to look like 1 over square root 2 pi sigma e to the minus 1/2 x minus mu squared over sigma squared. You'll notice right away the normalizing constants that don't involve mu, all the stuff that doesn't involve mu that's up to proportionality, you could just throw it away in the first place. Our Jeffries priors will always be defined up to proportionality. You would need to normalize them later. There's nothing in the information that normalizes things and said that they have to be probability distributions. Bayesians are using this contraption in a slightly different way than other people might use the information. So it was never designed necessarily to be a distribution, but it could be used that way. So we could get rid of this stuff. You'll just note when I take the logarithm of that, I'm going to have this additive term of this, and as soon as I hit it with the first derivative, it's going to go to 0 anyway. So we could leave it in if you want to see that. So this will look like minus expectation. we'll take this derivative, e mu squared, and then we'll have the logarithm of 1 over 2 pi sigma minus, and I'll do this in one step, 1/2 x minus mu squared over sigma squared. And so I just took log of this thing and added it to that thing. So the logarithm cancels out my exponential. So one question might be, which logarithm did I use? I used the natural log. If I used a different log, it wouldn't make any difference. So again, everything is defined up to proportionality, and all logarithms are just scaled differently from each other. So their asymptotic behavior is exactly the same. So once I take this first derivative over this is going to be a 0. So this would be expectation. I'll take my first derivative inside, so this will be a 0. And then I'm going to have this minus derivative over mu. So 1/2. I'm going to bring down my 2. X minus mu over sigma squared. And then I have to chain rule as well. I have to take the derivative over mu. That's going to change that to a plus. And we just take one more derivative. This will be, so that's just 1 right here. Derivative over x over sigma squared is going to be a 0. And then I've got this derivative of minus mu. And so that's just going to be a -1. And I divide by the sigma squared. That's constant. Remember, our expectation is over x in all of this. And so there's no x's there. So nothing to take an expectation over. And so, and we're in luck right here. This minus sign and that minus sign creates something positive. If this came out negative, I would know I've made a mistake. It's got to come out positive. If it comes out negative, either you made a math error or you applied Fubini's in a case where you can't apply it. So this will be 1 over sigma squared. So is this a constant? This is a constant. So it's a constant with respect to mu. So we set this as a constant. So this right here is just proportional to a constant. And so our Jeffreys prior on mu is going to be proportional to a constant. We're going to raise that to the half power. Constant raised to a half power is still constant. And my favorite constant is 1, so I'll just plug in 1 right here. So that's all proportional to 1. And so if you did this on psi, you would not come up with something flat. Instead, you would come up with something like, well, what we had just erased, the transformed version of mu. So we'll study that example in a second. Actually, I'll leave that one for you guys to do. The Jeffreys prior on psi might ask you in an upcoming final exam or something like that. Let's do another example. Let's do the Jeffreys prior for sigma squared. Now I'm going to call sigma squared v. So I don't want to be thinking about this as sigma and I'm squaring it with the operator. I'm thinking of sigma squared as a thing. So that's just a variable itself. So we'll just nickname it v. We'll write down that model. Does anybody know what the Jeffreys prior for this is going to be? I see at least 4 smiling faces. That usually means yes. Gonna take a whack at it? Some people are now smiling for other reasons. Eric, what do you think?
Gamma half-half.
Gamma half-half. Okay, so maybe. So gamma half is a contender, I guess. It's in the realm of reason. At least it lives in the right space. Anna? 1 over sigma squared or 1 over b. So let's just check. So this is going to be proportional to, I'll write this down, pi Jeff v. And so this is going to be equal to, it's actually proportional. Let's take 2 derivatives over v log 1 over root 2 pi. I have the v to the 1/2 in there. So I got to write that down correctly in terms of v. So usually I put a sigma right down there, but I want to write it down in terms of v. That's why I've gotten rid of the sigmas. So sigma squared, and then I take derivatives over it and all of that, and I'm raising it to powers. It'll look a little funny. So if I had sigma squared, you might not know what that is. That's the only reason we're changing it to v. E to the minus 1/2 x minus mu squared over v. So again, that part's not going to help us there. But we do need the v in there. If we would have tossed that, we'd get the answer wrong, because this depends on v. So minus expectation. I'll do my 2 derivatives here. Logarithm of this. So this is going to be minus 1/2 log v. Could have written this down as log v to the minus 1/2. Those are the same thing, so I'll just simplify everything. So minus 1/2 x minus mu squared over v. And this is raised to the 1/2 power too. This is a really easy place to make a mistake on an exam, and you just start rolling through and you forget to take the 1/2 power at the end. So this is raised to the 1/2 power. So let's just do our 2 derivatives. Try to get this part right. So this is going to be minus expectation. First derivative, minus 1/2. Derivative of log v is 1 over v. So that's pretty easy to work with. Minus 1/2. Then I've got this term right here, so I'll just flip it upside down, if you will. V to the minus 1. So break down our minus 1 right there. It's going to be there. Decrement v again, so this will be v squared down here. So x minus mu squared. If you'd like, I'll write it like that. So one more derivative. Make that v to the minus 1. All raised to the 1/2 power. This will be derivative of this. Bring down my minus 1, so this will be 1/2 v to the minus 2.
Did you not do it?
I need that, yeah. So d dv. Yes. So derivative of all this stuff. I think that one's good. Minus 1 comes down. Decrement again. This is going to be minus 2 over 2 x minus mu squared v to the minus 3. And now I need to take an expectation over all of this. Expectation. And then my 1/2. So X's aren't gone from all of this stuff. So this whole thing will look like expectation of 1/2 to the, I'll write it over here, b squared minus x minus mu squared over v cubed. Expectation can roll right over that. There's no x's in there. This is a linear operator, so I can throw my expectation right there. Get rid of that. And raised to the half power. So what's this expectation? It's recognizable. What is it? This expectation, x minus mu squared? What's that?
0.
Not quite. So let's just check this out. Expectation of x minus mu. Careful where the square is in that. V. So that's variance. That's the definition of variance. So that's V. Sigma squared is the same answer. So that's V itself. So sometimes you can just recognize what these things are, otherwise you have another calculus problem that you need to solve right in the middle of everything. So that's V. So this whole thing is going to be 1/2 v squared minus v over v squared. I'm kind of glad I did this a little bit. To the half power right here. So, sorry, that was cubed down here. That was v here. So I can change that. Get rid of one of those. And lo and behold, this thing is negative. I've made a mistake.
You put the minus sign in front of the expectation.
I forgot it all the way through, like down here. So I had gotten it all the way up here. I had that minus sign and then I erased it. So this was a minus sign out in front of here. There's a minus sign right in here too. So before I take the half power. And so we can easily see where we messed up and why it was negative. But it did give us a moment for pause. If it turns out negative, you made a mistake somewhere. And so this thing is just going to be plus 1/2 v squared to the half power, which is going to be proportional to 1 over v. So that's the correct answer. So does anybody know what happens when I transform this to phi scale? So if I invert it, what's that transform? Let's come back next time with that and close this up. So the Jeffreys prior on phi is going to be 1 over phi. And if I transform this over to phi, this would be 1 over phi. So, and that's kind of the whole point. So let's come back next time. Remember what answer we came up for v. We'll do it for phi as well. And then we'll show you the proof as to why a Jeffreys prior is supposed to be transformed in variance. And then we'll move on to hypothesis testing. Okay, thanks you guys. Be safe out there tonight. Lots of crazies.